So we finished that example off yesterday. And let's do another one just to make sure this stuff is sort of clear in our minds. There we go. It says graph a function y equals f at x that has all the following properties. We'll have some choices here. That bothers people sometimes. You're not used to choices in math. But we'll have some open choices. We can draw any graph we want as long as it fits these qualifications. So, first thing. These things are points. So let me write that again. Anytime they say f at negative 3 is 2 or f at 1 is negative 1, those are just points we put right on there. It gets us off to a great start on our graph. F at negative 3 is 2. There's a point. F at 1 is negative 1. There's another point. And already I've got a feel for what this graph might look like. I don't know. It might do something like this, up and then down through this point. Or it might, maybe it'll come down from here through this point and then continue. I'm not sure, but I got a feel already. 2 points is great information. Then it says increasing on the interval negative infinity to negative 3. Now you see what I said yesterday. This won't be confusing inside a question about whether it's a point or an interval, because it'll say right before it usually, oh, here's an interval. Now, this way of writing this is very convenient. I said yesterday you have your choice on which way you can write it. I don't care which way you write it, but you have to be ready that in a question they might write it either way. So you got to be ready for either version. But this is nice. It just says, oh, starting at negative infinity. So for our purposes, we talked yesterday that infinity is very complicated. Very, very, very complicated. Whole books on infinity. For our purpose, it's actually a little simpler. Negative infinity just means off our graph this way. Yeah, just big enough that it's off our graph. Really big, this way. So from negative infinity to negative 3, this thing will be increasing. So apparently it comes over here and it's increasing the whole time all the way to this point. How convenient, to negative 3, the point we already have. I think there's one question in the homework that doesn't give you a reference point. You get to decide how high or low you go. So don't be surprised by that. Don't be caught off guard by that. Some of them are really open-ended like that. But this one, I think we can see exactly what's happening here. Increasing all the way to negative 3. I like putting little check marks on these. If you have trouble with them, if the information is just all too much for you, just check them off as you go to make sure you did them. Then it says, and, what and? Oh, increasing on this interval and from 1 to infinity. So from this x value of 1 over to infinity, and for us infinity just means off our page. From 1 to infinity we're going to be increasing. Now yesterday we found out that it could be I've made a mistake there. I might find out later, oh, I'm only supposed to go down to 4. I got to go all the way down to 8. I don't know. I don't worry about that as I'm doing these questions. I just draw something and go, okay, that's right for now, and I'll fix it later if I have to. Oh, I did this, 1 to infinity. A common question on these when we do intervals is, oh, they say, oh, those are the x values. Yeah. When you have interval notation, these are both x values, a low x value and a high x value. Intervals are always given in x values. And then someone says, well, why is it always given in x values? Well, that has to do with where we're going with this. We're heading off to biology, chemistry, economics, these type of things. And this has a great chance of being time. So when we're saying, when is something increasing? This is literally when. From negative infinity up to time negative 3. It's usually a time thing. And so that's why we try to fit in with that right now, that we're always giving the x values as the interval. Then it says decreasing from negative 3 to 1. See, they switched notations on us within the question. Just to check, do you know both notations? And you've seen this before, and this was new yesterday. So it says from negative 3 to negative 1. So from x value negative 3 to x value 1. See, always x values on the interval. From negative 3 to negative 1, decreasing. So I got that. And then it says domain x element of reals. Oh, I got that, yeah. It's going on forever in both directions. I put arrows in the end. Maybe that reminds you to put arrows in the end. And range y element of reals. Oh, I got that too. So sometimes you get lucky and you're like, oh, so that's it. That's all I got to do. Somebody else says, well, then could I have increasing out of here? Could I just have, leveled off something like this and do an asymptote or something like that? And I go, yeah, you got openness here. Lots of graphs you could draw, but as long as you fit the qualifications given. What questions do you have about that one? More time? That's good. Then I think we go back to the PowerPoint for a while, do we? Yes. So So back to this PowerPoint here. And in the PowerPoint, if you go back, and that PowerPoint's online, it actually goes through and does those graphing for you. So if you look at the graph later and you're like, I don't know where he got all this stuff from, you can watch the PowerPoint. It goes, see, it puts all the points on in that example and draws a curve, and then it does the same for the second one. So it goes through it, and this one used straight lines. I used curves. You see you got some openness there. Or you can watch the video. The video goes through it all. New words. Continuity. A function is continuous on an interval if it does not contain any holes or breaks in that interval. There's lots of definitions of continuity. This is like a beginner one, just to get you started. As long as there's no holes and breaks, we say it's continuous. If it has holes and breaks, we say it's not continuous, or we say it's discontinuous. So a discontinuity occurs when there's a break in the function's graph. We refer to the location of the discontinuity by stating the x value. And again, we state the x value because there's a very good chance we're not going to use x, we're going to use time, and so we want to know when the discontinuity occurs. Now this is very related to the restrictions from last year. X can't equal 4 or something like that. And so we'll find out more. And if you're really curious about this, for now the base graph you've got that you can refer to in your brain when you're first learning about continuity, you could use this one. Let's get a different color for the graph itself. We'll go with, green. It'll be a Christmas graph, red and green. Okay. This one here, that's y equals 1 over x. It's one of your base functions that you're supposed to know. And again, if you're like, oh, well, I don't really know it, you're saying I'm supposed to know it, I don't really know it. The best way to get to know these things, build a table of values and see if you can create the graph. And then from then on, you probably won't ever forget it once you build a table of values once before. So maybe later, if we have some time, if somebody's like, oh, can you tell us more about a certain base function that we didn't learn enough about in grade 11? I'll build the table of values with you, if we get time later. Anyways, this one, there's 1 over x. And you see the break here? It's not all one piece. And so this thing's discontinuous at x value 0. It has a break in it. There are many types of breaks and holes, and we'll analyze those things. For now, we just got to be able to recognize them. Example. Here's a graph, and it should have arrows in the end of it. So I'm going to just add those. Please add those on your picture. Pointer options. Let's see, back to a black color here. This one is supposed to have arrows. The computer program we use to make up these graphs doesn't automatically put the arrows on, so sometimes the arrows aren't on our graphs in our PowerPoints. This thing has no discontinuities, no breaks, it just goes on forever. Reminds you of a parabola type thing. Parabolas just go on forever. There's no breaks in them, they're all one piece. We say later in calculus, we always talk about, can I draw it without lifting my pencil? Yeah? Continuous functions, you can draw the whole thing without lifting your pencil once. So you can't do that here. You draw the left side, and then you got to pick your pencil up and draw the right side. It's a weird little memory trick to tell you whether something's continuous or not. So this is continuous on the whole interval. Negative infinity all the way up to positive infinity. Now look at this one. Now, this is coming up. Yeah, this is like foreshadowing for you English people. This is the kind of graph we'll get to in chapter 5. And we'll be able to graph this fairly easily. I'll have a set of steps for you. It'll be like 6 steps. Do these 6 steps, and you'll be able to come up with these graphs. So I don't want them to intimidate you. I'm going to spend a whole chapter showing you how to graph these things. All we need out of this is, given a graph here, we look for the breaks. Where are there breaks in this thing? And there's a break. Do you see the break at -2 there? Yeah? It jumps at -2, and then it jumps again at +4. So we say this thing is discontinuous at x equals -2 and x equals 4. Those are called vertical asymptotes. You don't need to know that word in this chapter yet, but it's coming. Last year, you were supposed to see the word horizontal asymptote when you did this. Does horizontal asymptote ring a bell? Not really. Okay, so what a horizontal asymptote is it's an imaginary line that you can draw, and the graph approaches that. It's heading towards that line, but never gets there. Now, I got to be careful how I say that, because it's possible to go through asymptotes sometimes, and sometimes you can't, and we'll talk all about that in chapter 5. For now, just an introduction to the word. If there's an imaginary line in the graph that the graph approaches, we call that an asymptote. Okay? And again, it's not a word that we need in this chapter. It's convenient to use it, All you have to be able to do is go, okay, it's discontinuous at -2, and it's discontinuous at 4. Okay? Is there one more here? Oh. Okay, now this is where the knowledge of the base functions come in. X squared, we would like to know it well enough that we know that I don't know exactly what the shape of this thing is, but I do know it's a parabola. When I see that x squared, it clues me in that we're talking about a parabola. So it might be opening upwards, it might be opening downwards, it might be left, it might be right, it might be stretched. It can do all sorts of stuff, but we're talking about a parabola. And that's enough in my brain to be able to talk about whether it's continuous or not. I don't need to do any better than that. This didn't ask for a very careful graph because if you're right with me, drawing a very careful graph of this is a giant nightmare. You got to complete the square with a 3 out there. You're going to get fractions all the way through. This was like the tough question in grade 11, was to completing the square on a mess like this. But here in grade 12, we're like, well, I don't need to do all that just to answer the question, is this discontinuous? Because I know a parabola is continuous. There's no discontinuity. Notice I didn't draw anything here at all. It was all in my brain. I will, though. This graph, we need to get to the point in this chapter where when we see -3x squared plus 5x minus 4, we know it's some kind of parabola. And in this case, the negative out front actually gives me a little bit more information. That information being, this is a downward opening parabola. I don't know exactly where it is. Even I can't do it in my head to know exactly where this thing is. I'd have to do a little bit of algebra, complete the square, or quadratic formula to find the zeros. Just trying to throw that all in your brain so that you're like, oh yeah, all this stuff that seemed like just a nightmare in grade 10 and 11, but it could come up. Don't worry, I'll tell you when it does come up. I'll warn you when all that algebra, we need it. For now, what we need to be able to do is go, oh, parabola. Oh, continuous. Yeah? Because parabolas are continuous. They don't have any breaks in them. Okay? Let's go back to your base functions for a second, if this is freaking you out a little bit. We've got your, oh, we'll get to that one in just a second. I already talked about that one. Keep all that stuff. I want to show you the base function summary. And before you get freaked out about what you have to know and what you don't have to know here, let's find that base function summary. Is it before properties of functions? It must be. Oh yes, base function summary. Here we go. And let's talk about how many functions we know that are discontinuous, that have a discontinuity in them. Lines don't have any continuity problems. Parabolas are all one piece. See, most of the functions we know are all one piece. Can I, hey, I'll just do this then. Ooh, come on now. I'm getting scared now. My computer's known for resetting itself. When it stops responding like this, that's about the time it resets itself. I'll use the computer over here so I don't blow this thing up. Oh, it doesn't want to do it. Oh, there we go. Now it's back. It's just moody, that's all. Okay, y equals root x. No discontinuities. It's only over here, but there's nothing discontinuous. It's all one piece, okay? 1 over x. We just talked about that one. That's the one we have to worry about. That's discontinuous. Down here, exponential functions, not discontinuous, all one piece. Absolute value, all one piece. So pretty much everything we've seen so far will be continuous. So what do you got to worry about is just, where's the PowerPoint? All you got to worry about is a function I might give you, where you just have to look at it. I give you the graph. And this one. That's your discontinuous graph that you got to know. When you look at that, you go, whoa, whoa, whoa. I know that's discontinuous. And this is where the knowledge of the base functions is important. You got to know when I write y equals 1 over x, you got to be able to go, yeah, this thing. I remember now. And then you can talk about that it's discontinuous at x equals 0. It's got a jump at x equals 0. Jump's not the right word, actually. Jump means something else in math. And we'll get to that. But for now, it's a handy word to use. Questions about discontinuous and continuous functions? More time here? Well, you didn't have to write anything, did you? No, you're just playing along. All right. Little note here. The definition of continuous functions is slightly more complex than the definitions above and will be considered in future lessons. I mentioned that. the definition here, a function is continuous on an interval. I said this is like an introduction to continuous. We'll come back to continuous in chapter 5. We'll come back to continuous in calculus big time, and we'll really get to the bottom of continuous. But for now, it's enough to go, okay, is it one piece or is it multiple pieces? That's all. That'll be good enough for now. Symmetry. Okay, this we got to be careful with, because this is not the toughest concept, but it might sneak up on you if we're not careful here. A function is an even function if f at negative x equals f at x for every value in the function's domain. What does that mean? Oh, man. Let's just back out of here and do a separate example for just a second. I've got some paper ready to talk about this for a second. I want to talk about the graph y equals x squared. And within this, I'm showing off how to use table values. Let's just pretend for a second you got to the test, and I asked about y equals x squared, and you went, I don't remember y equals x squared. I don't know what goes on. I don't know how to graph it. You know? So you just take a second, you take a deep breath, and you go, okay, Mr. Todd said table of values. Well, the table of values in a calculator, you can graph anything. It just might take you a long time. That's all. Oh. And you put in some numbers. You go, -4. When I square -4, I get 16. You just put that right in your calculator. -4 squared is 16. And then I'm going to do -3 squared is 9. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. How long does that take, really? No time at all. See, you've got this emergency move for graphing, which is just you break out the table of values, you get your calculator going, and here's one good news about COVID and school during COVID. Instead of having an hour and 15-minute period for tests, we can extend that a little bit. So if you ever need a little time on a test, we can handle that during COVID, which we couldn't handle it too well in other courses, right? Or when we're in regular semesters. Okay, so when I go to graph this, I'm going to graph the points carefully because I really want to get to the bottom. This is an even function, and I really want, by the end, to go, I totally get what you mean by even now, okay? I'm going to start graphing in the middle, and I'm going to graph 0, 0. And then I'm going to graph 1, 1, and -1, 1. And I've already shown that this thing looks like it might be even. That is, if I go over to 1, I get a y value of 1. If I go to -1, I also get a y value of 1. It's even on either side. That's not why we use the word even here. That's why we use the word even. But it works out really nice that it sort of crosses over. We can use that as a memory tool to go, oh, it's the same on both sides. And for the parabola, y equals x squared, that happens all the way up. 2 is 4, -2 is 4. See? It's even. It's the same. Every x value, okay, here's the important sentence. For every x value, if I plug in the positive number, I get the same y value as if I put in the negative x value. That happens every single time, making for a function that looks the same on this side as it does on this side. It's like a mirror image of itself on either side. We call it even. We say any x value you plug in, you'll get the same y value as if you put that negative x value in. And that's what this PowerPoint was trying to say. To be even symmetry, if you plug in a negative x value, you'll get the same answer as if you plugged in the positive x value. Either one you plug in, you'll get the same answer. And what does this mean? I just explained that. If you evaluate the function at any number and also the opposite number, you'll get the same result. For example, f at -2 would give the same result as f at 2. And when you want to talk about even functions and you're like, I want to be able to visualize even functions, I really suggest using the in color. I really suggest in your mind when you want to picture an even function, picture the parabola. It's the perfect even function, and it's perfect because you've seen it in grade 10 and grade 11 a lot. The graph is symmetrical about the y-axis. See, the y-axis splits it in half, and it's symmetrical. It's the same on either side. The graph does the same on the left side as it does on the right side. Examples of even functions. Here they go. Any parabola will do actually, as long as it's only been moved up or down. As soon as you move it left or right, it's not even anymore because it doesn't stay the same on either side. The axis has got to be right down the center. Weirdly, cosine is even. It's the same on the right side as it on the left side. And I nudge you about cosine. We got a whole chapter of this coming. There might be questions in the homework or in examples for this, but I'll be kind and I won't put any trig on the Unit 1 test. Yeah? Oh, can I do it off a table of values? Oh, here, big test moment here. Let's have that awkward moment where you stare at it for a second and decide for yourself. Would you be able to decide if that's even, or can you see why that is an even function? What is it about the values here that make this even? They're the same, yeah. If you go to 2, you get 16. You go to negative 2, you also get 16. So even functions do that. And finally, this one. Okay. After my awesome explanation, hopefully it was awesome, I hope that I was like, oh yeah, I got it. This is trouble, okay? Now, 2 things I want to tell you. I know that it is an even function because all the exponents are even. Yeah? That's what even actually means. That's what they're referring to when they say even. The exponents are even. And when we go to do odd, all the exponents are odd. And there's a homework question about that, where you go, okay, is this an even function? And if all the exponents are even, the answer is yes. How do you prove it, though? It's really difficult. Like, even to prove y equals x squared is even. I did 1 and -1. I did 2 and -2. I did 3 and -3. I did 4 and -4. It really looks like it is, but I didn't actually prove it. Let me go back and prove it. No, don't start that. I don't want to do that yet. I want to go back. Thank you. No, keep that. Go back to here. Somebody says, okay, well, prove it, Mr. Todd. Prove it's always true. It really looks like it is. I totally believe it is, but you got to prove it. Here's what I would do. And still, you see that move I just did? My daughter is using her iPad, her iPad. Wouldn't that be nice? Using my iPad to do her notes at school, and she's learning about how to do that on an iPad, and she's doing all her notes on an iPad. Yeah? She says she's not quite fast enough to keep up with a regular lecture, but on the video lecture she's getting right now, she does, and makes these beautiful notes, saves them to the cloud. Beautiful system. So, if you don't have a Christmas gift picked out, maybe an iPad would be great fun. Hold on. Where was I? Oh, proving this is always even. Maybe you're already convinced. You're like, this is enough for me. It absolutely looks like it's always going to be even. Here's how you actually prove it, though. You go f at x equals x squared. Yes? And then what you do is you go, well, what happens if I sub in a negative x instead? Instead of trying 2, 3, 4, 5, I'm saying any x value you want, any negative x value you want, you sub it in there. And so you'd get, I'd sub in negative x into the function and square it, and I'd get x squared. See, negative x times negative x is positive x squared. It's the same. Therefore, it's even. That is not an easy move because it's sort of a theoretical algebraic move. So, the first time through, what I want to say to you is, if you want to prove something's even, sub in negative x and see if you can get the original function back. Because if you do, then it doesn't matter. Subbing in negative x gives you the same as if you subbed in positive x. Now, why does it always work? Let's go back to the PowerPoint and show the slightly tougher example. Okay. Why does it work? We go, okay, let's sub in negative x and see if it always happens that I get the original function back. When I sub in negative x, every time I see x, I put in negative x, and all the even powers exactly cancel out the negatives, right? Anytime you have an even power, you're going to have an even number of negatives, which will turn into positive, and I get the original function back, and so it's even. That is difficult. So what questions do you have about this proof? What can I tell you more about this? Last night, I watched my phone carefully. I had it nearby the whole night, and I got no texts or emails from you. Now, you don't need to text or email me. I'm not lonely. I'm not sitting there going, oh, forlorn. I had lots to do. I took care of my time. When I didn't get anything, when I woke up in the morning, I went, okay, there's a few possibilities here. One, the homework all went so well that they're like, oh, I don't have any questions. That's good. Two, you browned out. We call it browning out at our house when you really try to get something done, but nothing actually gets done. You stare, the famous one is your homework's in front of you, you got your phone right there, and you don't feel quite as guilty about not doing your homework because you're sitting beside it, which is, that's insane, right? You're better off taking a break for half an hour and coming back to it. But anyway. Maybe you browned out and didn't get any work done last night. Maybe you didn't even look at the work last night. Or maybe you're scared to text or email me. I encourage you to try. Even if it's a question you're pretty sure about, you just want clarification, try and see what kind of response you get. Don't suffer in silence. In class too. Don't suffer in silence. Practice something. Practice a frown, a little shake of your head like, no good. Or just raise your hand and go, no, could you just go over that one more time? Yeah? When you need to. Because otherwise I'll just cruise right on and go, okay, is that okay? And I'll just keep going. We only have 5 weeks together. We don't have time to play around here and play footsies with each other and try and figure out if you're going to ask me questions or not. And it's hard because I come bursting out of that desk. Yeah? And I come up here and I have all this energy, and you're like, it's almost like you're sitting at your desk like this going, well, I don't want to ask him. I hope the people yesterday found out when they asked me a question, what did I do? I jumped all over it. Oh yeah, let me show you. And I promise what I'll never do is I'll never do something like, well, I just showed that to you. How can you not know that? I'll never do that. I'll assume it's me every time. I'm like, oh, I must not have explained that very well. Here, let me go again. All right? Any questions about this? Oh, good. When you do an even power on something, I'm going to lecture you a zillion times about this, so I can erase this. Let's use an actual number. Okay? When I go -2 squared, we get -2 times -2, and a negative times a negative is a positive. And the negatives sort of cancel because there's two negatives to cancel out. And this happens every time when you do an even power. Let me do a big one. -2 to the power of 16, -2, -2, 3, oh, here we go. I chose too big a number. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And so this negative times this negative, that's positive. This negative times this negative, that's positive. Positive, 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 positive. And we get all these positives. Only happens for even powers. Odd powers are always going to come out to negative, but even powers always come out to positive. So I don't even care, negative x, what the x is. I just know that when I put negative x here and go power of 4, the answer is actually going to come out to be positive. And here, this one's going to come out to be positive, except there's a negative out front. And the 7, well, the 7's not really relevant in all this. And see what I get back is the original function. And what I find out is subbing in a positive number gives me this. Subbing in the exact same negative number gives me the exact same thing. And so it's even because it doesn't matter what x you put in. If you put in 2 and -2, 10 and -10, 40 million and -40 million, you'll get the same thing both times. Better? Questions? It's the problem with math, right? What's weird about the next year and a half in math is that the individual lessons, you'll follow them and you go, I totally get it. And then these little details are what's going to set you off. And those are the things you have to ask about. And you feel like maybe it's not a great question. No, it's the perfect question. Because the idea of even, I can walk up and say even, say on both sides. Good? Okay, see you later. That's not the issue. The issue is all these little details from previous grades, and you've got to nail those things down. Odd symmetry. Exact same thing, except odd. So I want to show you an odd function that's going to come up next chapter. And more practice on showing you about table of values and how unbelievably powerful it is. I'm going to show you this function, which you haven't seen before, and you're not responsible for this chapter. Okay? So I'm not adding a new function here. I'm introducing one that comes up a little bit later. Okay? I'm trying to remember exactly when it comes in. Well, later. Okay? Not a function we need right now, but I'm using it as an example of an odd function. And let's say I asked for y equals x cubed. I'm not going to. On the test, and you're like, y equals x cubed? I don't know how to graph y equals x cubed. Well, yeah, you do. You just choose some x values sub them in and see what answers you get. So I get negative 3 cubed, I get negative 27. Then I get negative 8, negative 1, 0, 1, 8, 27. You can see I know this function pretty well. You know, we've been hanging around together for, well, when did I learn x cubed? When I was your age at 17. So, you know, got a 30-year relationship going here with y equals x cubed. That's why that goes so quickly like that. And let me graph these points. Now check this out. 0, 0. Sort of reminds you of x squared. Starts in the middle like this. 1, 1. And you're like, hey, this is just like x squared. Look at it, it's going like that. You go over here. Negative 1. Oh. Negative 1, negative 1. This way. See, it's the same, but it's not the same. Like, it's like this side, it's flipped over here, but then it's flipped again. Like, it's like on this side, you get the same number, but you get the negative version of it. And it happens every single time. 2, you get 8. Negative 2, you get negative 8. My next one goes right off the page because x cubed just grows like crazy. It just goes right off the page. But you can see, draw this carefully, like that, like that. And we call this odd. It's still symmetrical, sort of. It's like flip this way, then flip that way. Some people say, well, it's actually been spun around the axis like this. That's what odd functions are. And where does the odd come from? Always happens with odd exponents. Yeah, with odd exponents, you're always going to get the same answers, but negative. Boop. Oh, okay. Yeah. An odd function, if you plug in the negative, then you get the negative answer. You always get the negative version of the answer. If you evaluate the function at any number and also the opposite number, you get opposite results. For example, f at negative 2 would give the opposite results of f at 2. So the graph of f at x has rotational symmetry, we say. You know, I don't really like the rotational just means, okay, it went from here down around to there. I like flip, flip. That's the way my brain works, but maybe rotational works better for you. The graph does the opposite on the left side as it does on the right side. Here's some examples of odd functions. Hey, 1 over x is odd. Yeah? It's the same over here, but it's been flipped down there. It's been rotated around the axis. Sine is odd. That's going to come up in chapter 6, is that when you go to the negative side of sine, you get the exact same thing, only it's negative. You know? When this one's positive, this one's negative. When the right side goes to negative, the left side goes to positive. There's a table of values. You see, this is the exact same table of values from the previous slide, except that instead of being positive on the left side here, or on the right side here, they've gone to negative. How do we prove it? At some point, you get to the point where you're like, oh, all odd powers. It's odd. They're all odd powers. To actually prove it, though, you'd actually have to sub in negative x. Wherever you see x, do some work, and see when you cube a negative, you end up with negative. This one's negative, and you'll see this is the exact same thing, but all the signs have been changed. And if all the signs have been changed, then we're talking about an odd function. Me personally, I don't ask this proof until calculus. I'm just sort of introducing it here. It comes up in the homework, but I don't know. It's a little much on an advanced function unit 1 test. So try these out in the homework, but don't freak out about these just yet. Yeah? And behavior. This is important. And behavior is what do these functions do as they go off the page. You already know some end behavior. You know that y equals x squared gets big on both sides. You know that y equals x gets big but opposite. One goes positive, one goes negative on both sides. So here we go. When we talk about end behavior, we want to know what happens as you go off the page this way and what happens as you go off the page that way. That's our version of infinity. Our version of infinity is go off the page, off the graph, either way. So for instance, this function, it needs the arrows. Let me get my arrows going here. I don't want red arrows. I want black arrows. There we go. Okay. This function, as you go off the page this way, as x goes to infinity, the y values go to infinity. As you get big x values, you get big y values. And if you're having trouble with infinity, substitute the word big for now. That'll be good enough. So as x gets big, y gets big. As x gets big and negative, so as we go this way, big negative x values, I get big negative y values. I'll do one more and then I'll pause for questions. This one. As x gets really big and positive, the y value gets really big and negative. As x gets really big and negative, the y value doesn't keep getting bigger. The y value seems to go to the number 3. That's weird. Yeah, that's sort of new to us, that it would just settle into a number. But we'll see more and more like that as we go along. Oh, I said I pause for questions. Any questions about what I wrote there? You're just basically writing what happens as x gets big and what happens as x gets big and negative. And you just write what happens. Does it get big or does it head to a number of some type? Questions? Ooh. Absolute value. These are, again, the type of question that somebody will come up and they'll say, Mr. Todd, do I have to graph this to be able to answer the question? And I always say, well, if you're asking that question, then yes. Graphing is the great bailout. You know, you're like, well, if I just graph it, I'll be able to get the answer. And so it's a great move. Sometimes we can know the function well enough. If I said y equals x squared out loud, hopefully you know well enough to know, oh, it does this. I don't need to graph it. Really? Well, you did. You did graph it. You knew it. You just knew the graph well enough. But if you get a function like that, then you'll have to go through and graph it to get its end behavior. Oh. Sort of implying, this PowerPoint's sort of implying that we should be able to do this in our head. Let's try it. Let's try and do it in our head without actually graphing it. What does absolute value function look like just by itself with no transformations? We know the awkward pause is by design, right? The awkward pause is to let your brain go, do I know this? He's acting like I should know this. Do I know this? And if you do know it, then great, you got it in your head when we compare answers here. If you don't know it, then it's your chance to go, geez, I better nail that down, because he acts like I should know it. It's just a V, yeah. It's a lot like a parabola, it's just like a V. Now, I'm just talking about end behavior, so all I care about is where my hands are pointing here. And let's just talk about the transformations without actually regraphing them. The -3 outside now is going to go like this. Yeah, more of this in the transformation lesson coming up very shortly. Then left 6, that doesn't really change the end behavior. Up 8, that really doesn't change the end behavior. And now my end behavior looks like this. As x goes to infinity, the y values go to negative infinity. As x goes to negative infinity, the y value goes to negative infinity. And that's why that example is acting like you should be able to just do that in your head. I'm not acting like you should be able to do that in your head. No, if you got this question on a test, you go, just give me a second, all right? Let me just... Okay, I got the graph. Answer the question, all right? So if you're stuck, yeah, graph them. For sure graph them. Absolutely. Oh, was that the last one on that page? Any questions on this? If you're like, I haven't done enough of the absolute value homework, I don't really know how to graph those yet. Yeah, that's no problem. When you get to that, this question will become much easier because you can just graph it. And I'm going to do transformations in a minute, and that should really help. Bringing it all together on a separate page. No, not on a separate page. Switch over to, if you look at your lesson worksheet, we did 2 examples there. If you flip to the third, number 3, all those questions that are on the PowerPoint are there. And so I'll switch over. Let's see if we agree over to this worksheet. Do you got this? Yeah? This is basically a review of everything. If you're like, I'm sort of lost in all the details. Okay, this asks you to do everything that was in this lesson on a bunch of given functions. Let me just put the arrows on this thing. Please put the arrows on. On the test, I'm always very careful to make sure you know whether it's got dots at the end or continues on. Here's some space for rough work if I need it. For now, domain. The x values keep going in both directions forever, and the way I write domain is I write these really fun curly brackets, and then I write x element areals. That's my fancy way of writing. Oh, and if you want to be able to write that fancy R like me, you draw a line straight down. Then you start your R just a little bit back. See how fancy that is? I don't know. You can just write R. I'll live with it. But if you want to be able to draw the fancy art. And these are fun. Yeah? Just take some time and learn how to down, around. Yeah? Fun brackets. It's good. And then range y element of reals. And this is just our fancy, easy way to write all the x values. You can have any x value you want, and the result is you'll get any y value you want. Intervals of increase and decrease. Okay, now the PowerPoint does it with a full fill-in thing. I'm going to do it with the way that you'll have to do it, like on a test or something like that, is just with a highlighter. So we're going to highlight in red where it decreases. So it decreases. Oh, that's too big. It decreases. No, that's still too big. There. There's decreasing. And then again, it decreases in there. Me personally, I don't then highlight the increases because I can see them. They're highlighted by not being highlighted. So here's the intervals where they increase and decrease. So here we go. Increase is in the non-highlighted spot between -2 and 2. So I'm going to write -2 less than x less than 2. Decrease. Two different intervals. Over here, when the x values are less than -2, and again, when the x values are greater than 2. You can use a comma there for now. Later in calculus, we'll use a little U, a little union symbol saying these two sections, the union of them, but we don't need to do that right now. Are there any questions about that, about the increasing and decreasing? Just remember, go left or right when you're looking at these. But hey, let's do them with the new notation. Sometimes it's better, sometimes it's not. If we want from -2 to 2, we just write -2 to 2, just like that. Lower and upper. It's not confusing with a point because they asked us for an interval. And so clearly, if I'm giving this answer, it's not an interval. Oh, sorry, it's not a point. It's the interval. I'm answering the question. X less than -2. Oh, better draw a line across there. So I'd write -infinity to -2. And then 2 to infinity are my two intervals there. You can write it either way you want. You can even mix and match. You could say, I'm going to answer the first question with this one. And I'm going to answer the second question with this one because I understand that better. It's whatever you want to do. Okay. Absolute max and min values. What's the absolute highest point it gets to? I phrased that question in a way trying to trick you. None. Not infinity. I know I'm throwing infinities around here like, can I just say infinity? No, you can't say the max is at infinity. I actually didn't even say in here that it goes all the way to infinity. I didn't include infinity. So you can't include infinity. It seems like nitpicking, but it's the beginning of starting to be able to deal with infinity. Local max and mins. Oh, we do have local max and min values. Here, f at -2 equals -3. That's a min. And then the max is f at 2 equals 3. Continuity, always continuous. There's no breaks in this graph. Symmetry. Okay, well, let's just wait a second here because that I taught fairly deeply yesterday. I'm hoping that's all pretty straightforward, but the symmetry might be a problem. And on the test, I think I use the words comment on the symmetry. I leave it open to you. I don't just say, is it odd, even, or not? I actually just say comment, and you got to know the words. When I say comment on the symmetry, we're looking for odd, even, or neither. So I'm going to put those down here in your note. Here are our choices. Odd, even, or neither. And I'm just going to circle one of these. Does anyone want to take a shot at it? To know whether it's odd, even, or neither, just looking at it? If you're having trouble, let's start with even. I think that's the easiest one to look for. Even means it's the same on this side as it is on this side. Is it? No, it's not the same. I see some head shaking now. Well, I know it's not even. Well, let's take that out of there. Not even. So it's now either odd or neither. Every time I do an x value, when I go to this side to be odd, it means that I get the negative of what I get on this side. It's just flipped again. So it's like flipped, flipped, or it's rotated around. Sometimes you have to look at individual values and go, okay, well, let's see. 1 is 2, -1, -2. 2 is 3, -2, -3. So is it odd? Yeah, it's odd. It's the same on the left as it is on the right, except it's changed from positive to negative. That's the best sentence I've said of that so far. End behavior. We write two sentences. We say, as x goes to infinity, and we write as x goes to -infinity. If you're having trouble with infinity, substitute the word big. That will do for now. Yeah? As x gets really big, so we're heading this way. As I go more and more this way, what happens to the y values? What kind of y values are you getting? Say it again. As I get big x values. So when I get x value 4, 5, 6, 7, what kind of y values do we keep getting? What's big negative y values? So the way we write big negative is we write, oh, this computer wants to break on me. Every time I press something, it does the little thinking symbol. Big x values gives big negative y values. How about big negative x values as I go this way? -5, -6, -7, -8. What kind of y values do I get as I go out there? Big positive y values. Here's how we write that. And it is totally awesome if every time you see the word infinity, you just think big. Think really, really big. Any questions about that? That's all we're doing the rest of the way. We're just going to keep doing those exact same things with all sorts of different functions, so you're ready for these questions for all sorts of different functions that we'll see. Questions here? More time? Let's do it again. New function. Oh, it's supposed to have arrows there, so put the arrows on. The arrows are really important to let you know that this thing keeps going all the way like this. Domain issues. No, sorry, what is the domain? The x values, it just keeps going out and out and out and out. So I get to do my fancy brackets. Woo! Get to do my fancy E, line, around. You don't need to do the fancy R, but it's fun. How about the range? Is there some restriction on the y values here? Yeah. We've got to be greater than or equal to -6. We've got to stay above -6. So I write that like this. Y element of reals such that y is greater than or equal to -6. I've seen this written in reverse before, where you write y greater than or equal to -6 such that y is the element of reals. I think that's technically wrong, but I don't really get too excited when people do it because it's a weird notation. Intervals of increase and decrease. Me personally, the way I handle is I just highlight all the decreasing. So there's decreasing, and I don't have to highlight the increasing because I can see the increasing where it's not decreasing, it's increasing. Could it do neither and go straight across like this? Yeah, I guess it could, but you won't really see that very often. It'll either be decreasing or increasing. So it decreases. Oh, I'll do increase first. Between -1 and 0, and then for x greater than 1. And then it decreases x less than -1, and then between 0 and 1. The other notation, you'd go negative infinity to 0 and 1 to, not negative infinity to 0, that's not right. Negative 1 to 0 and 1 to infinity. And decrease, you'd go negative infinity to negative 1 and 0 to 1. Again, you got your choice between those two notations, whichever one you find easier to work with. Absolute max, absolute min. Does it have an absolute max? No, there's no highest point here. We don't say absolute max and infinity. That's not a number. It's not something we can quantify like that. Absolute min, yes, there is some absolute mins here. F at negative 1 equals F at 1, and those things equal to negative 6. There's multiple ways to write that. That's one way to write it. It's sort of a convenient way to write that. But you could write, it has an absolute min at two different spots, negative 1 comma 6 and 1 comma negative 6. So you can write that a different way. You don't have to choose my way to write it. I'm pretty open there. It's not like there's one proper way to list points like that. There's certainly not. Local max and mins. Let's see, local max. 0, negative 5. And the local mins are negative 1, negative 6, comma 1, negative 6. So I've listed those this time so you can see there's another way to write that. It's just to write the points. Now let's really try and pick your brain for these things here. Continuity. Is this thing continuous, or does it have a discontinuity? No, it doesn't. Yeah, it's continuous. Continuous everywhere. Symmetry. Your choices are even, odd, neither. Who wants to take a shot? Whether it's even, odd, or neither. Yeah. Same over here as it is over there. Just flipped right over the y-axis. Even. Fair warning. On the test, I didn't give you these options. I didn't say even, odd, neither. I just said comment on the symmetry. Your job to know my choices are even, odd, or neither. And behavior always starts the same way. You write as x gets big, as x gets big and negative. You always write those two things. You say, okay, what happens as I get big, positive? What happens as I get big and negative? As we go big positive, what kind of y values do we get as we go farther and farther out here? Big y values. And the same happens on the negative side. Both of those go to positive infinity. You're going to see me do this dance in a couple of days. We're going to talk about all sorts of different graphs, and we'll be like this, like this, like this, you know. And so when it's both up like this, positive infinity on both sides. I think it's cute that I thought I was going to get through this whole lesson yesterday before he left. No chance. Questions here? More time? I'm addicted to saying that. I can't stop saying it. Oh, here we go. Look at this now. Look at the level of difficulty jump here. Like, here, what do you think about this graph? Let's just get used to all the language, all the different things, and then here, now it's like, oh, y equals 1 over x minus 4 plus 3. You got to be able to graph this thing to then answer all the questions. So this is actually an introduction to transformations. This is the graph of y equals 1 over x. This is where the rough work comes in. the base function is 1 over x. You can sort of see it there, 1 over x minus 4. But then two things have to happen. The 1 over x function has to move right 4 and up 3. And if on a scale of 1 to 100, you're just like, I only sort of understand where you're getting those numbers from. Well, don't worry. I got a lesson coming out that's doing transformations the whole time. Where does that come from? A plus 3 outside the function means move it up 3. A negative 4 inside, weirdly, means move right 4. That's very strange. So instead of the 1 over x function, which we normally are used to seeing sitting in these two quadrants like that, the whole thing's been moved right 4 and up 3. The best way to graph 1 over x is to just redraw the new asymptotes. If it's been moved up 3, I'm going to choose orange. My goal with orange is that you can just barely see what I'm about to write. Can you just barely see that? Maybe it's better than just barely see it, yeah? Since it's been moved up 3, that asymptote, that line that 1 over x approaches, has been moved up 3, and the other asymptote has been moved right 4. That makes graphing 1 over x really easy if you just draw those two lines on there, because it's going to look like this. And it's going to look like this. How does it look? Does it look like 1 over x just moved right 4 and up 3? Yeah? And those lines really help frame what's going on. So we go back to that question that was answered, that I made up and answered earlier, which I said, Mr. Todd, do I have to graph it to answer this question? And the answer almost as always is yes. Graph it, and then you'll be able to answer the questions. Domain. A new type of domain here, because we're just going to state one x value that x cannot be. X can't equal 4. And in grade 11, you were supposed to do a bunch of stuff with restrictions. You know, at the end of the question, you always had to say, oh, comma, x can't equal 2, x can't equal negative 1. Don't panic if you don't remember all that. We'll talk a lot more about it in Unit 5. But for now, it's just like, the reason it's 4 is that I can't divide by 0. So the x value of 4 would make this denominator 0. Like, do I need to know all that? As long as I can graph it, doesn't that give me the answer? Yeah, it does at this point. You don't really have to do that algebraically. You can do it right off the graph. Range. Strange range here. Y element of reals such that y can't equal. There's one y value that this thing can't equal. 3. So that's strange and different, and why this example is in here. And this is very weird too. Increasing and decreasing. The graph 1 over x, check out this part. Decreasing, always decreasing. This part always decreasing. This thing never increases. That's very strange when you look at it, because it looks like it's all over the place. But if you actually look at the graph, you'll see it always is going down. And it jumps here. Starts back off at the top, and it's always going down. When is it decreasing? It decreases for x less than 4 and for x greater than 4. And you might go, doesn't it just decrease everywhere? No, not at 4. 4, it doesn't even exist. There's nothing there at 4, so it doesn't do either. No absolute max or mins. No local max or mins. You see me staring at the calendar? As the clock ticks along here, I'm staring at the calendar going, okay, well, what am I going to do next? I'll tell you what I'm going to do next. I'm going to take a survey as soon as I'm done here of where you're at with your homework, and then make a decision about how many times I'm going to teach, and then we'll decide when I'm going to teach today. Okay, so it's all on my mind. Did all that to give you some time to think about continuity. Is this thing continuous everywhere? No, it's got a continuity problem. Discontinuous at x equal to 4. That matches up with the domain issue up here. Yeah, and chapter 5 will definitely put those two things together. We'll say domain issues are the discontinuities. Those two things are the same thing. Symmetry, none. And then these two sentences. As x goes to infinity, as x goes to negative infinity, and this one's very fascinating. As x goes to infinity, the y value heads towards 3. And as x goes to negative infinity, the y value heads towards 3. So it doesn't have to be infinities that this thing heads to. It might head to a specific number, and here that specific number is 3. Question? It's a great question. It's the perfect question. Doesn't it look like it's symmetrical? It looks odd, but it's got to be odd around the axes in the center here. The fact that it's been moved over here messes that whole thing up. So that happens with y equals x squared too. As soon as you take y equals x squared and move it over, it loses that symmetry around the axes. It has to be around those axes. Those mirrors have to happen around the axes. Perfect question. Yeah, for sure. Has to be perfect. Yeah? Perfect question. Absolutely perfect. I'm going to refer back to what I said is that we're sort of getting ready for biology, chemistry, economics, all these things, where this axis is probably time. So let's imagine the only really good application I can think of discontinuities in those things would be something like physics, where this could be the voltage. And you say, where does the voltage? You'd say, at time 4. You wouldn't say at voltage 3. You'd give the time, and that's why we give the x. Could we give the y? Yeah, it's not necessarily wrong to give the y, but we're preparing for the idea that this x-axis is probably the independent variable of time or number or days or something like that, and so we want to know when. Yeah, if you want, this is answering when is the discontinuity. When should I expect this thing to happen, whatever this thing is? Yeah? Good question. Other questions? Oh, that's heartening that I got questions there. It makes me believe that you'll ask the questions when they come up, but that overall things are going pretty well. Okay, how many more do I got to do? Still 3 more to go. Oh, great stuff, though. We get to explore 3 more types of functions. Beautiful. I pressed the button. There we go. Okay, check this thing out. Nightmare coming. F at x equals negative 2x squared plus 12x plus 5. Graphing this is really, really, really difficult. Unless you know how to take this and turn it into its vertex form. Yeah, going back, you've been taught this in grade 10 and grade 11, but it's not the type of procedure that sticks in people's brains, I got to tell you. It's the type of procedure people memorize, puke out on the test, and then it just leaves your brain because it's not something you use a lot. So here's the steps to this. This procedure is called complete the square. Do you remember those words from your nightmares? Eh? Step 1. Common factor out the coefficient off the x terms. It's not wrong to common factor it out of the constant term. It's just a waste of time. And I'll show you at the end why it's a waste of time. So don't imagine that that's a must move. It's just really convenient to do that. Now, here's that magic move. The magic move is take half of this number and square it and add and subtract that. Some teachers come up with this fancy phrase. Half it, square it, add it, subtract it. And they say it really fast, and hopefully it'll stick in your brain. Do you kind of remember this? I'm seeing nods and shake your head. Yeah, okay, good. If you didn't see this, like, you're so lucky in one way. Like, when I was in school, you go home at night to do your homework. And if you didn't understand how to do something, the only source you had was the notes you took in class, or the textbook, and that was it. Or you could, get this, call someone on the phone. Yes, I'm still from those days, you know. Call a friend on the phone. Hope they were there. No, sorry, Bob's not home right now. You're like, oh, crap, yeah? You guys, you're like, but I don't know how to complete the square. Nerds created the internet. They're everywhere. It's infested. You go on to Google. That was looking for this. Complete the square. I click on videos. Oh, Khan Academy. Those are the best ones. Okay, I'm not going to play it, but you see, like, bang, bang, and you can get a lesson on complete the square. Maybe you don't feel lucky that that information is out there, but I can tell you, you're the only kids in history who have an unbelievable reference sitting right there for these things. Not that I'm not going to teach it. I'm going to teach this very carefully, but if it's really just goes right past you, like, I don't remember this at all, get it checked out, because complete the square is going to pop up its head up once in a while. Okay. Common factor out the leading coefficient. Then this magic number. And I'm going to try and explain the magic number in just such a way that when I'm done, you'll understand why we chose the number we did. Here's how you get the magic number. The explanation of why we choose it will come later in the example. The magic number, you take half of this number here, -6, which is -3, and you square it. So the magic number is 9. So I'm just going to add 9. And everybody freaks out at that time during complete the square because they're like, you're just going to add 9 to things? You're allowed to just add 9? No. I definitely am not allowed to do what I just did. The only way I can add 9 is also to subtract 9 at the same time. Now that's a cute trick in math. You can add 0 anytime you want, and that's what I did here. I added 9 and subtracted 9. And you go, well, that seems pretty stupid. You know, why would you add 9 and subtract 9? And here's why. Take a look at this for a second. And this is why in the reviewing the basics, it got you to factor a little bit, because you got to sort of remember how to factor these things. We're looking for two numbers that add to 9, or sorry, multiply to 9, but add to -6. Just give it a second, let it bounce around a little bit. We want two numbers that when you multiply them together, you get 9. But when you add them together, you get -6. It's -3 both times. It's the perfect number to complete the square. 9 was the perfect number to make it that when I factored this thing, I don't get two crazy things. I get the same thing twice. Now the square is completed. That's why that number was chosen. If you choose this exact number, half of the coefficient squared, you'll get exactly what you need to complete the square. Why do you care about that? Okay, well, I got to do a little bit more multiplying here. -2 times the -9 is +18. And then I got the +5. Why do I care? Okay. When quadratics are given like this, they're not very convenient. When they're given like this, it's very convenient because now it's all set up for transformations. It's all set up to be able to do those transformations on it. It's the graph y equals x squared, moved right 3, up 23. If that stuff's just slowly coming back, that's okay. I'm doing a whole lesson on it sometime today. Yeah? I implied it was at 9 this morning, but it's not happening, right? So right 3, up 23. Now there's not enough room in my graph, so I'm just going to put it up there. Right 3, up 23. And this negative says I'm opening downwards. I'm just going to label that point. There wasn't enough room in my graph to do the whole thing. but it's enough to get a nice sketch of the graph, which will be enough to be able to answer the questions. Here's a good news, bad news sentence coming at the same time. Yeah? It's a test hint, and sometimes test hints are great, and sometimes test hints are like, well, it's nice that I know it's coming. It's going to be some work now to get it figured out. There'll be a question on the test where you're going to have to complete the square. Yeah? So you're like, oh, maybe I'll go watch those videos tonight. And oh, maybe I won't. Hopefully I've motivated you to go, I got to be able to complete the square. Here's my promise to you. I'll keep this coefficient under control. If you go back to look up some complete the square stuff, you'll see that if that coefficient's like a 5 or a 4.2 or fractions pop out of this thing, things go crazy with fractions. I'll keep it like this one, sort of under control. Be like a 2 or a 3, and this will be like a 9 or a 10. You know, like something pretty well behaved. Okay. Theoretically, the rest of these answers are easy once I can graph this thing. Here it goes. Domain. X element of reals. Range. Y element of reals such that y less than or equal to 23. Intervals of increase and decrease. Increase for x less than 3. Decrease x greater than 3. Absolute max and min. Max 323. No min. Local max and mins. Max 323. No min. No discontinuities. Not symmetrical. As x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. I did that really fast on purpose to try and establish that to complete the square is the important part here for parabolas. If I can complete the square and get a graph of this, the answers to parabolas are pretty straightforward. Then I'm going to pause for questions, and I'm definitely going to force myself into answering 2 important questions about this. My first question for you is, a few minutes ago, I sort of acted like parabolas were all symmetrical. This parabola is not symmetrical. What is it about this parabola that forces it into the situation that's not symmetrical anymore? As soon as it shifts off the x or off the y-axis, it's not symmetrical about the y-axis anymore. I'm just going to tidy up my writing here. What questions do you have about the parabola? You got my good news, bad news hint about the test, the good news? You know there's a question where I got to complete the square. I'll get marks for completing the square. Bad news? I got to know how to complete the square. Yeah, so you're going to have to get that narrowed down. Yeah, good question. This negative 2 out front is multiplied by this whole thing, which got factored. But it's also multiplied by that negative 9. Here's a good question. If you really want to understand the complete the square, you got to be able to answer this question. Where's the positive 9? Where'd it go? What's that? Yeah, it's inside here. If you took x minus 3 and expanded it out, you'd get this stuff back here. So it's hidden inside that squared bracket there. So it's there. It's just we needed it to complete the square, and now it's hidden inside this x minus 3 squared. If that's really confusing to you, just expand this out, multiply it all back out, and you'll get back to this. This is the same equation as this. It's just written in a different form, a very convenient form, which is vertex form, which allows me to find the vertex and graph this thing. Yeah? Other questions? 2 more examples I got to get through. I definitely got to hit that 10:35 mark here. Right? I got 2 more examples to go. It's been good, though. I think I've taught a lot of the transformations within here. The transformation lesson could go quickly because of this. Oh, absolute value. Here we go. I got to take an absolute value function. I got to do a bunch of stuff to it. Now, take a look what the question asks here. And I want to talk about the difference between sketching and graphing. Sketching is I just need a basic shape of this thing so I can answer the darn questions. Graphing is like, no, they asked me to graph it. I've got to get a perfect graph here. Okay? I'm going to try and draw a sketch of this thing and convince you that I can sketch this thing very quickly with my knowledge of absolute value. Absolute value function. That V shape, right? The -4 out front means now it's like this. Yeah? That's a vertical reflection and a stretch. But I don't actually care about the stretching all that much. And then this is like a stretch or compression, but I don't actually care about that all that much. And then moved up 8. I think this is a pretty good graph to use to answer the questions. Oh, I'll do straight lines just to make it somewhat. Don't let me continue unless you're convinced that that's a pretty good graph of this situation. Pretty good sketch. Let's be careful with the words there. When we say graph, we usually mean make it perfect. Sketch is like, let's just get the basic shape here so I can answer the darn questions. Absolute value. Vertical reflection, that negative says point downwards. If you're like, I sort of know that, that's okay. Transformation lesson coming. And then moved up 8, so it's up to here. Now I can answer this whole thing. Domain, X, element of reals. Range, Y, element of reals, such that Y is less than or equal to 8. Intervals of increase and decrease. Increase, X greater than 0. Nope. X less than 0. Decrease, X greater than 0. Absolute max and mins. We got an absolute max at 0, 8. No min. Same here, max. 0, 8. No min. No discontinuities. I'll do the end behavior and I'll wait on the symmetry and let you give you a chance to think about it. Let me just get this word going here because we use this word in math all the time. Was a sketch instead of a graph. A graph, I would have been like very specific, got the exact points, got exactly the right graph. And if we were asked to graph, you should do that. And in transformations lesson, I will do that carefully. I did a sketch here so I could answer these general questions about the graph. I said, okay, y equals absolute value of x looks like this. This thing has been flipped because of that negative out front, so it's pointed downwards like this. It's been stretched or compressed. But I don't really care about that for the answers I have to give. And then it's been moved up 8, so I took this upside down absolute value and I moved it up 8 to there. Does that help? You're right. There's definitely some stuff missing there if I needed a very specific, perfect graph of it. Yeah? And we'll talk about that more in the next lesson. Questions there? Okay, here's the test question on symmetry. Ready? I'm not going to tell you what the choices are. I'm just going to say comment on the symmetry. What's the symmetry of this graph? What, no, stop. What are the choices? What are my 3 choices for symmetry? Even, odd, or no, there's no symmetry at all. Which one is it? It's even. It's the same on the right as it is on the left. It's even. It's a perfect word because it's even on both sides. Even though that's not why we use the word. We use the word because of exponents, and y equals x squared is sort of an even type thing. Do you have questions about that? Yeah, it could be that this thing actually looks like and I'll just make up another version of it. Maybe it actually gets stretched, compressed. Maybe it actually looks like that. And I argue that doesn't change any of the answers that it's asked here. Yeah, so you're right. If you do need a more specific graph, then you're going to have to take those things into account. I'm sort of glossing it over it here because I'm going to beat that to death in the transformation lesson. Yeah? More time here? More time? One last example. I know you're wearing down here. And then I gotta finish this fast enough that we can have a quick conversation about how I'm going to teach the rest of the day. So I'm going to do the same thing here. I'm going to gloss over the transformations. If you're like, I'm only sort of with you on how you got that sketch, that's okay. I'll do more of it in the next lesson. Here's the sketch of the graph. Base function is y equals 3 to the x. It would sort of look like this. Y equals 3 to the x. That's not what I want here because it's got a horizontal flip there. So it's going to flip this way and move up 2. So I don't want that graph. I want this graph. That's what the graph of this thing looks like. It's moved up 2, and it's been flipped horizontally. So now the going off to infinity goes this way. The going to 2 goes this way. Like I say, more of that next lesson. Once I have a nice little sketch of it, I can do these answers. Domain x element of reals, range y element of reals, such that y is greater than 2. Intervals of increase and decrease. Always decreasing. Absolute maximum min, none. Local maximum min, none. Continuity, no discontinuities. Symmetry, none. Weird end behavior. As x goes to infinity, y goes to the number 2. And as x goes to negative infinity, y goes to negative infinity. And if coming up with that graph is like, wow, you really just zipped right through that. I need a little more information there. Yep, whole nother lesson coming on transformations. Weird first chapter here because the order of it, you might go, well, why wouldn't you do the transformations first before you did these other lessons? And there's good and bad choices about this chapter. Maybe transformations should have been right after domain and range. Maybe that would have been the right time for it. But by the end, we'll get it all the pieces tied together. I hope I got through it well enough.